Unmasking On-Policy Distillation. Where it helps, where it hurts, and why. Published by Apple on May 12, 2026. Look, on-policy distillation is a standard post-training technique, but until now, we haven't actually known why or when it works at the token level.
Right, and the paper drops 3 core insights that totally change how we should be building these pipelines. First, distillation guidance really only helps when the student model is on an incorrect reasoning path.
So if it's on a correct path, the teacher's just, what, adding noise?
Exactly, just stylistic noise. Second is the comprehensibility hypothesis. Small models need full step-by-step reasoning generated by themselves, while larger models can actually use concise summaries or bigger external teachers.
And the third one?
It's about when to show mistakes. Putting a wrong demonstration in the prompt hurts performance on simple tasks, but it actually acts as a vital alignment booster on super hard math problems.
Welcome to AI Paper Podcasts. If you are an AI researcher, an ML engineer, or, just building and training models, our mission in this deep dive is to really unpack the math and the methodology behind these findings.
Yeah, because for a long time, the industry has just treated distillation as a black box, right? You take a student model, you feed it a teacher's distribution, optimize for forward KL divergence, and just run massive amounts of compute.
Right, and then you just look at the aggregate metrics at the end and hope they went up.
Exactly. But those aggregate metrics hide all the granular token-by-token dynamics of what's actually happening during training. Yeah. To really grasp what Apple's team solved here, we have to look at how standard distillation objectives actually work under the hood.
Right.
Take generalized knowledge distillation, or GKD. It minimizes the forward KL divergence from the student's probability distribution to the teachers at every single node in a generation tree.
The assumption being that if you perfectly mimic the teacher, you get optimal performance.
Yeah, but the reality is that this objective treats every single token disagreement as equally important, which is a huge problem.
The researchers have this great bookshelf analogy for this. So imagine a math word problem. A bookshelf has 3 shelves, each holds 4 books, and 5 are removed.
Right.
The student model starts generating and says, so total is 3 plus 4, but the teacher model evaluates that exact same prefix and decides it prefers, therefore, 3 times 4.
Yeah, and standard distillation algorithms just blindly average out those corrections. The gradient update for the word so versus therefore is mathematically weighted the exact same as the update for plus versus times.
Which is wild because one of those is just the stylistic quirk. The other is a catastrophic reasoning failure. Like if the student uses plus 4, it fails the task entirely.
Exactly. Standard distillation doesn't know the difference.
It's like a GPS that screams with the exact same urgency when you take a scenic route as it does when you literally drive into a lake.
That is a perfect way to put it. So to fix this, we need to isolate the true mathematical direction of task success, completely stripped of whatever stylistic bias the teacher has.
And the researchers did this by deriving what they call the ideal per node gradient, right?
Yeah, the ideal per node gradient. They basically stepped back from specific training algorithms and created a theoretical oracle. They asked, okay, at this specific token position, what exact parameter update will maximally increase the student's probability of reaching a correct final answer?
Completely ignoring what the teacher preferred.
Right, completely ignoring the teacher. But doing that requires mapping the downstream binary outcome, so success or failure, all the way back to the continuous logit space of the current token choice.
Which they did using the softmax Jacobian.
Yes. It calculates a gradient that increases the logit of its specific token only if picking that token leads to a success rate higher than the average success rate from that current node.
Wow.
It's just a pure empirical measure of utility. Mm-hmm. And what makes this really compelling for folks listening is how it intersects with sparse reward RL. The paper literally proves that a specific variant of GRPO recovers this exact ideal gradient in expectation.
Now wait, standard GRPO has per trajectory length normalization, right? You divide the advantage by the length of the generation so that long, rambling reasoning chains don't just dominate the loss landscape.
Exactly. But Apple's team showed that if you remove that length normalization, creating what they call Dr. GRPO, the expected objective at any single node cleanly reduces to a function of the student's probability of picking a token and the empirical probability of that token leading to success.
So the math perfectly aligns with their oracle gradient.
It does. They essentially established a ground truth metric for what a parameter update should look like, based entirely on empirical success rates.
Which is awesome in theory, but for the engineers listening, setting up an empirical oracle gradient based on success probabilities sounds like an absolute computational nightmare.
Oh, it is.
I mean, we're talking vocabulary sizes of, what, 150,000 tokens? Sequences that are hundreds or thousands of tokens long? Computing success probabilities for every branch at every node means mapping an infinite generation tree.
Yeah, you would need more compute than exists on Earth for a single prompt.
So how did they actually do this without infinite compute?
They engineered their way out of it using a targeted rollout algorithm. So
Yeah.
instead of mapping the whole tree, they use exponential depth windows. They partitioned the reasoning chains into segments.
Okay, how does that work?
Well, early in the generation, say tokens 1 through 50, the reasoning paths branch out a lot, so they sample densely. But deeper in, past token 500, the model has largely committed to a logical path, so they sampled much more sparsely.
Budgeting compute by depth makes a lot of sense, but even within those windows, there are way too many tokens to explore. How did they pick which nodes actually get the rollout budget?
They allocated it strictly based on the magnitude of disagreement between the student and the teacher.
Ah, okay.
Yeah, they rank nodes by calculating the GKD gradient magnitude and the absolute difference in token probabilities. If the student and teacher really strongly disagreed on a specific token, the researchers forced the student to generate multiple full completions from that exact prefix.
To see definitively if that branch led to a win or a loss.
Exactly. And because every deep rollout naturally passes through all its ancestor nodes, one single completion enriches the empirical data for the entire path above it.
It cascades. That's really elegant. But still, running these rollouts to build a success tree and then rerunning it for different teacher models to compare them, that has to burn through an astronomical amount of GPU hours.
It would have, but they used this brilliant trick: teacher-independent tree sharing.
Okay, break that down.
Basically, the generation tree and the empirical success probabilities on each node are just a function of the student's policy and the environment's reward. The teacher's preferences don't actually change the student's tree.
It's like rendering a massive 3D environment in a video game, right? You render the physics and geometry once. Then you can drop 8 different players, or in this case, 8 different teacher models into that exact same world without re-rendering the whole thing.
That's exactly it. In phase 1, they built one massive enriched generation tree using just the students' rollouts. Then in phase 2, they passed that single tree to 8 different teacher configurations.
So each teacher just does a single forward pass over the established nodes.
Right. And that architectural choice reduced the total compute required by about 7x.
Wow. Even with the 7x reduction, the paper mentions this took 72 A100 days, right?
72 days. And the output of all that compute is a single foundational metric they call the gradient alignment score.
Which is the cosine similarity between the theoretical ideal gradient and the actual distillation gradient from the teacher.
Exactly. If the score is greater than 0, the teacher's gradient is pushing the model in the same direction as the empirical success vector. The teacher is genuinely helping.
And if it's near 0,
it means they're orthogonal. The teacher is burning your gradient budget on stylistic noise that doesn't actually help solve the task. And if it's below 0, the teacher is actively sabotaging the student.
By pushing it away from a path that actually works. Okay, so now that we have the alignment score, let's look at the data. They tested the Quen3 model family, right?
Yes, specifically the 0.6 billion and 1.7 billion parameter models on the Boole Q and MMLU datasets. And the first major finding is huge. Distillation exhibits substantially higher alignment on incorrect rollouts than on correct ones.
Let that sink in. It works better when the model is wrong.
Yes. The mechanics of the gradient space explain it perfectly. When the student is on a correct reasoning path, the reward gradient is super weak because, well, the model's already optimizing for the correct outcome.
So the teacher's intervention there is just stylistic. It's like a driving instructor. If you're driving perfectly down the center of the lane, the reward vector is 0. But the instructor is sitting there nudging you to put your hands at 10 and 2 instead of 9 and 3.
Right. It's low utility noise.
But the moment you swerve into oncoming traffic, the incorrect rollout, the reward vector, spikes wildly. And the teacher grabs the wheel.
Exactly. The teacher knows how to solve the problem. So it produces a massive gradient vector pointing away from that failure. The vectors align perfectly.
Which implies our standard pipelines are wildly inefficient. We're spending massive amounts of FLOPs updating weights on correct trajectories where the teacher is basically useless.
Exactly. Distillation is fundamentally a rescue tool for failing paths.
Okay, so if it's a rescue tool, who should the rescuer be? The dogma has always been, use the biggest, smartest teacher you can find, Hook a 1B student up to a 70B teacher.
And this paper proves that intuition is severely flawed. The effectiveness of the teacher depends entirely on the student's parametric capacity.
Really, bigger isn't always better.
Not at all. For the tiny Quen 3.6b student, self-distillation dominated everything else. The highest gradient alignment came from the 0.6b model itself, prompted to provide a raw, step-by-step correct demonstration. They call it Self-1C.
So when they tried giving that tiny student a summary or pairing it with the big Quen 3.8b teacher, what happened?
The alignment score just plummeted. But, and this is the crazy part, when they ran those exact same teachers on the slightly larger 1.7b student, the hierarchy completely inverted.
Oh, wow. So the 1.7b model liked the bigger teachers.
Yeah. The 1.7b student saw its alignment nearly double with summarized demonstrations. And on BoolQ, the external 8b teacher outperformed every self-distillation variant.
So why the flip?
The researchers call it the comprehensibility hypothesis. A gradient signal is completely useless if the student's architecture lacks the capacity to parse it.
So a 0.6 billion parameter model just literally cannot comprehend the logical leaps made by an 8 billion parameter model.
Exactly. The massive teacher's reasoning trace is essentially encrypted to the tiny student. The gradient updates push the student's parameters in directions that just don't map to its internal representations.
It needs the verbose step-by-step trace in its own voice to learn.
Right. But the 1.7b model has almost 3 times the parameters. It can decode the condensed logic of a summary or bridge the inferential gaps of an 8b teacher.
So you really can't just blindly pair a small student with a huge teacher. The teacher has to operate within the comprehensibility bounds of the student.
Exactly.
Okay, but BoolQ and MMLU, those are pretty short reasoning chains. What happens when things get really complex?
That's where the AAAA 2025 case studies come in. This is a benchmark of incredibly difficult math problems. We're talking reasoning traces that range from 5,000 to 30,000 tokens per generation.
30,000 tokens for one problem. So when they applied those same 8 teacher configurations to Abe, did the comprehensibility hypothesis hold up?
It did, but it revealed a massive contradiction regarding wrong demonstrations. On BoolQ, showing the student a wrong demonstration alongside a correct one in the prompt, the Self-1C1W configuration was just disastrous.
It confused the model on simple reading tasks. Right, it degraded the gradient signal and lowered alignment. But on the 30,000 token AIM problems, Self-1C1W achieved the absolute highest gradient alignment of anything they tested.
Wait, so showing a documented failure alongside the correct solution was the best way to teach advanced math, but it was toxic for basic reading.
Yeah.
I guess if you think about the geometry of the latent space, it makes sense. On a simple trivia question, the path to the answer is super direct. A wrong answer in the context just clutters the space with noise.
Exactly.
But a 30,000 token math derivation is basically a minefield. The space of possible logical failures is astronomically huge. So a wrong example acts like a bounding box.
A contrastive signal.
Yeah, it highlights a highly probable dead end, basically telling the model, hey, do not step on this specific logical landmine. And the model desperately needs that warning for such a long generation. Spot on. And it scales with the comprehensibility hypothesis, too. In complex math, the contrast between a flawed step and a correct step gives the model a high utility delta it can parse. In a simple task, that delta is just incomprehensible noise.
Which raises a huge logistical question for you if you're building these pipelines. How do you filter your training data to ensure the teacher's signal is actually aligning with the task reward without running, 72 A100 days of rollouts for every batch?
Because nobody has the budget for that. So the researchers looked at divergence metrics to see if they could act as a cheap proxy for gradient alignment.
Like forward KL divergence or Jensen-Shannon divergence?
Yeah, and L2 distance. And the data did show a consistent positive correlation. Higher divergence generally means higher gradient alignment. The useful distillation signal really lives in the zones where the teacher heavily disagrees with the student.
Because if they agree, we're back to injecting stylistic noise on correct paths, and the alignment score drops to 0.
Right. But here's the catch. The correlation is statistically super weak. The absolute value of Pearson's Raoult across these metrics is less than 0.05.
Ouch. So high divergence is necessary for learning, but it definitely does not guarantee it.
Exactly. The teacher might strongly diverge from the student, not because it's guiding it to task success, but because it's pulling the student toward a totally different, equally catastrophic failure state.
So Jensen Shannon can tell you an argument is happening, but it can't tell you if the teacher's side of that argument is actually useful.
Right. Divergence metrics are just a cheap filter to find where learning might happen, so you can discard the perfectly aligned tokens. But they can't reliably predict actual task success.
Okay, so we've covered the ideal per node gradient, teacher-independent tree sharing, the fact that distillation is a rescue tool, comprehensibility limits, and the power of negative examples in long context math. Let's bring this all back to actionable engineering for our listeners. What should you actually change about your training pipelines tomorrow?
The biggest takeaway is that you need to stop looking for a universal distillation recipe. The optimal context completely depends on your student's capacity and the task difficulty. If you're tuning a sub 1 billion parameter edge model, drop the massive external teachers. Use self-distillation with really verbose step-by-step traces.
And if you're tackling coding benchmarks or hard math with 30,000 token chains,
Then you absolutely must integrate negative examples into your self-distillation context to provide those contrastive bounding boxes. And broadly, you need per task, per token diagnostics. You can't just rely on aggregate benchmark scores anymore.
Right.
And most importantly, since the data proves alignment peaks on incorrect rollouts, the industry needs to pivot to rollout-weighted distillation. Focus your compute and your gradient updates strictly on the trajectories where the student is actively failing. That is the only place where the teacher's signal provides high-utility alignment.
Amazing. Thank you for joining us on this deep dive into Apple's latest research. But before you get back to your own pipelines, I want to leave you with one final thought. We established mathematically that on correct paths, the teacher's gradient vector is just orthogonal noise, wasting FLOPs because the student is already succeeding.
Yeah, just overriding the student's latent preferences for no reason.
Exactly. So imagine engineering a dynamic gating mechanism into your loss function. What if the distillation penalty is algorithmically zeroed out the moment the student model's internal confidence in a success trajectory crosses a certain threshold?
Oh, wow.
If the student strongly predicts a win, the pipeline just shuts off the teacher's influence for those specific tokens. That wouldn't just save massive amounts of compute. It could actually prevent open weights models from suffering mode collapse.
Keeping them from losing their own epistemic voice to a massive external teacher.
Exactly. Let the teacher intervene when the model swerves, but let the model drive when it knows the route. Something for you to experiment with in your next training run.